Good evening, everyone. Welcome. Thank you for your patience. We had the robots put the slides together, so we had to do a few things up here. I'm Catie Newell. I am an assistant professor here at Taubman College. I'm also the director of our Masters of Science programs for the Material Systems and the Digital Technology programs. I'm one of the co-chairs of the ACADIA workshops this year, along with Wes McGee, who's here to my right. He's also an assistant professor here at Taubman College and the director of our Fabrications Lab. And we are extremely honored, and speaking on behalf of all of the Taubman College team, to be hosting ACADIA this year, and very grateful to have the workshops here as well. We've been extremely grateful for the energy that has been around our Fab Lab and across the street at Pierpont for the last 2 days. It's been amazing and intense, especially this afternoon. Great production has occurred, and I think it's an amazing set of outputs that are now swinging us into the ACADIA conference. We'd like to do a few acknowledgements as well, of course acknowledging ACADIA for everything that's happening in the setup with this. We'd like to as well acknowledge Autodesk, who's been the primary sponsor of the workshops for this year. We also have some media sponsorship from Archinect. You will be able to see a podcast that has occurred discussing the workshops, as well as a series of 5 blogs that will be posted that will discuss the workshops more fully and an overall discussion of that as well. We would most certainly like to also acknowledge the staff of the Fab Lab. They have been incredible in helping everything occur this week. I don't know if they're sitting in here, maybe. Dustin, Asa, and John have all been incredible in giving their time and resources to help us with that. And we certainly also want to acknowledge the staff at Taubman, who has been doing a lot of the behind-the-scenes work to keep things together. Kate Granfield, Katie Cole, and Denise McGee, if you guys are in the room, much thanks for that.
And so I thought we'd start out by introducing all of the workshops that went on over the past 3 days. And then the panel members are going to do a little presentation more in depth on their workshops. But Catie and I, when we started putting together the list of workshops this year, we really tried to balance some kind of innovative fabrication workshops along with people who were doing exciting things with software as well. And just going through the list, the first workshop was led by Dave Pigram. I kind of co-led the workshop along with Dave, so it's been a busy week. Dave Pigram is coming to us from he's a partner in the firm Supermaneuver and is currently a visiting researcher at the Block Research Group at the NCCR and has a full-time appointment at UTS Sydney as well. The second workshop was led by my partner at Matter Design, Brandon Clifford, who's an assistant professor at MIT. And his workshop was titled Floating Megalith, so we're excited to see the results of this afternoon. The third workshop was led by Lauren Vasey and Giulio Brunello. Lauren's coming to us from the ICD, and Giulio's alumni of the iTech program at ICD and is now, I think, pursuing a PhD at the UCL Bartlett. Lauren's also an alumni of Taubman College, so it's quite exciting to have her back this week. The fourth workshop was led by Assistant Professor Sean Alquist from Taubman College and also Andy Payne from Autodesk Research, titled Interactive Textiles. Neither one of them is joining us on the panel tonight, but definitely be sure to check out some of Sean's work in the exhibition opening tomorrow night down at Liberty Annex. The fifth workshop was quite a big team here, led by Nathan King from Virginia Tech, Nick Coate from Autodesk, Matt Jezyk, who's also joining us on the panel tonight from Autodesk, Gustav Fagerstrom from Walter P. Moore Engineering, and Steve Lewis from Walter P. Moore Engineering. And Matt's going to go over a few details from all 3 of these workshops in just a few moments. The sixth one, Design, Space, Construction, Defining, Optimizing, and Communicating, was led by John Haymaker from Perkins & Will, Hakeem Hassan from Perkins & Will, Mohammed Aslil from Autodesk, and Wei Yan joining us from Texas A&M, the text being right over the picture. Hard to read. And the seventh one, Computational Bim in Practice, Conrad Soban from Grimshaw and Nate Holland from MBPJ. So we're pretty excited to have such a really kind of all-star lineup of workshop chairs this year, and I really think the output was pretty exciting to see today. It was a pretty big energy in all of the workshops, and we're excited to let the workshop leads describe them to us. So we're going to go straight into.
We're going to start with Dave.
Yeah. So if Dave, you want to come up and set up? We're just going to do a few minutes from each of the panelists, just to kind of go over, maybe frame the conversation a little bit, and then.
Thanks very much, guys, and thanks very much for the invitation. It's really great to be back in the building. So as Wes says, I run the design practice called Supermaneuver, which really has its history in self-initiated projects, mostly focused on fabrication-aware and other forms of form finding and computational design. At the moment, I have the great privilege of being the researcher in residence at the NCCR in Zurich, or in Switzerland, host of the block research group at the ETH Zurich. And I assume we'll hear from Russell at some point about all the things going on there. When asked to run a workshop, at first, of course, the most exciting thing for me is actually to be back working with Wes and to take advantage of the amazing facilities here at Michigan and all of the tools and workflows that Wes has put together within that. But of course, I want to try to tie all of those opportunities to a longer history of work that looks at the use of form finding, and especially fabrication-aware form finding in architecture. So I'm very excited right now to have been working for about 3 years on this project, which is getting very close to construction. So it's a 2-story penthouse apartment for a research agency in Switzerland. And the thing that's most relevant here is this thin shell concrete roof. So it's an average of 15 millimeters thick for each of the 2 shells of concrete. So it's basically a concrete surfboard. And the big innovation, apart from that it uses very little material, is very expressive, I hope you'll agree, and complements a lot of energy and integration aspects of the project. The fabrication method actually is all about minimizing minimizing formwork and scaffolding, and it does that through having a tensile network. That tensile network is effectively cables stretched between a rigid frame. And so that sort of basic standpoint is also the basis of the workshop, where we're using printed tensile networks, stretching them, and then using those to avoid the normal issues in architecture. It's scaffolding. In 3D printing, it's support medium. And in both cases, you really want to minimize them because they're painful and expensive in various ways, either from actual cost, indirect costs. For example, in this project, the ability to avoid scaffolding allows us to work much more quickly on site because we can get in under the roof and already be working and implementing, and especially in this case, scanning also the project to continue working. In previous projects, we've tried to avoid scaffolding in other ways by building aggregative structures where discrete post-tensioning allows us to work and build up and have self-supporting structures. Here, using flexible formwork in order to produce doubly curved structures with only using flexible fabric and 2D cut, very low-tech molds. So it's been a long-term fascination, basically, to try to use issues of geometry to avoid complications. So you still end up with something that's doubly curved. It's more or less a prerequisite if you want to make materially efficient structures, structurally informed structures. They are, by definition, non-uniform, and so you always have this problem of how do you create them in an efficient way. So in the workshop, the apparatus is a robotic held extruder. So we have the benefit of having the 2 robot work cell here in Michigan and the very large heated bed that Wes has made. And the idea is that we can try to avoid the normal problem of 3D printing, which is that it takes way too long and that you have to wait for not only the printing but also the support medium by printing very sparse nets very, very fast in 2D, and then taking those nets off the heated bed, allowing them to slump, not knowing, of course, exactly what shape they will take, and so then having to discover that. We can simulate and test. So here you see the kind of very sparse network covering a lot of area quite quickly, and then hanging that. So this is the process then of the robot, the second robot, because we're spoiled around here, which picks up the scanner and, of course, with a 2D laser line scanner, generating 3D data via the robot's motion itself, which then allows us to grab a point cloud. The point cloud is great, but it's not quite easy to follow. There's about, what is there, 1 million points or something like that here. So the first step is to mesh that with a classic Delaunay algorithm to do a length cull and then find the naked edges. Once we have the naked edges, we can divide those by a certain number and run a medial axis finder and recoup the center lines of the original network and the holes, which allows us then to know exactly where that is. In the tradition of all of my workshops, I guess, we aim high and inevitably finish just before the end, beaten by the post. So watch this space. We're ready, we've scanned, we know exactly where the net is, and very soon, in fact, on the next bigger net, then the idea is that we come through with a second material, carbon fiber reinforced polymer, and rigidize the structure so it will then be set in place. So as a stand-in for the concrete, which is also not quite there yet in the NEST project. I'd like to say, as I go through just a couple of images of where the end of the workshop is, or the end of the notional kind of trajectory set up by the workshop, I'd like to say a huge thank you to the workshop participants. We really came into the workshop not having done any of these processes, and so being really generous and also asking a lot of the workshops, but also expecting and being rightfully proven that they are incredibly smart participants and really, really energetic. And so we managed to go a huge, long way with really all of the key parts made by the workshop participants. So I'd like to say a huge thank you and congratulations to my guys. And with that, I'll hand over to Brandon. Thank you.
I'll go next. Hi, everyone. I'm Brandon Clifford from Matter Design and MIT. And in our practice, we construct a variety of scales of projects, but each dedicated to developing and bridging the gap between the virtual and the physical world, which is a rather broad category. But I'd like to talk about one of the trajectories which is leading towards the workshop which we took part in this week, which started with Periscope Foam Tower on the left. Periscope Foam Tower was robotically wire cut here at Michigan almost 10 years ago, I think, Wes? 7 years ago. But it launched a research trajectory for us, asking the question of what would it mean to re-engage the topic of volume in contemporary fabrication of architecture. And the following body of work slowly and incrementally folds in other disciplinary topics, such as structural concerns in La Voûte de Lefebvre, acoustic concerns in round room, and thermal concerns in microtherm. Each one of those pragmatic and performance criteria for those projects is undone a bit with the McGee Megalith, which was sparked by a completely different way of thinking about performance, one of theatricality. And this started with the discovery by Carl Lippo and Terry Hunt that the moai of Easter Island were in fact walked across the island into their final resting positions, and that these statues were in fact engineered to walk, not engineered to stand. And it's an interesting conflation between art and engineering. This is something that I'm quite fascinated in. And now we're talking about the workshop. This is a simulation of a buoyant megalith. That was designed by Matthew Johnson, if Matt's in the room. The question here is, can we simulate and design through organic modeling the ability to, right in here, there's a pocket to fill with water, to redirect the center of mass. So you can see the center of mass here, and the center of buoyancy there is dynamically being solved through this simulation to predict through the design process that this is what you would have if you just launch this thing into the water. And if someone, specifically if Adam, because we knew Adam's mass is to sit on the butt of this megalith, you would get this as a simulation. So you can see the center of mass has shifted back significantly, and we get a more horizontal condition. Just want to note, because this is an elevation, the section through the torso is a perfect circle, meaning it's not stable in rolling. However, the back is quite wide, so the back is your stabilizer. And Matt was instructed to sit on a single point right here, roughly. And of course, we 5-axis milled this. Maybe I'll speed through this process here. So this is the first half that's being milled. Thank you, Dustin, for all your hard work. And let's get to the launch. So you can see the scale of this is a bit like the size of a jet ski. This is not loaded at all. This is just empty foam. So you can see the tail is kind of hovering out of the water, but you can also still see our hook to connect to the rope. And this is the loaded condition. So the tail has lifted up out of the water. There was a significant leak. So I think it was slowly moving back down. And then here's Adam. He stayed dry in this video clip. We asked, I think on Tuesday, if anyone would volunteer, and Adam volunteered. So it's totally a volunteer effort. Here you can see the beginning and the rough end. There's a moment where he decides to put his hands forward, right there. So I really enjoyed the week. Thank you for having me. And also thank you to the participants. I know it could be perceived as a ridiculous task to engage a design process with which we're going to just construct a floating megalith. So thank you so much for engaging in this way of thinking. And with that, is Lauren or Matt? Okay, thank you.
I'm Lauren Vasey, and I'm from the Institute for Computational Design. And I was joined in the workshop by Giulio Brugnaro, who was one of our iTech master students who graduated and is now actually pursuing his PhD at the Bartlett. And thank you very much for the invitation. It's really good to be back here because this is also where I did my master's and where I learned to program robots with Dave and Wes. So at the ICD, we have two primary research interests. One is the is computational design, as it kind of challenges characteristic methods of design, and as well as computational connection to fabrication technologies such as robots, which allow us to challenge conventional ways of making. So just some precedents about the kind of work that went behind the kind of robotic weaving agenda that we were pursuing in the workshop is this idea of behavioral fabrication. So it's basically fabrication that's made possible by sensor feedback and interconnectivity between devices, people, and machines. And so what we're looking at is trying to program robots with behaviors rather than instructions that are like blueprints or notational design systems. So this was first investigated by a project, the Research Pavilion 2014-2015, which I presented last year at ACADIA, in which we were looking at both agent-based behavioral design methods as a means to mediate between performance criteria, fabrication constraints, but to produce kind of the robotic paths for, or fiber layout for a final design of a research pavilion, which was basically a pneumatic inflatable which was reinforced with carbon fiber. And actually the robot is also programmed with behavior. It's basically force sensitive, so it knows when the force is too high and it can adjust its path based on this kind of environmental data that it's getting back. So I teach, in addition to teaching the design studios for the research pavilions, I also teach behavioral fabrication in both a kind of advanced robotics course as well as a thesis topic. So we've defined kind of 4 trajectories. One, biological role models. Biological role models are very interesting because they don't require a high level of knowledge about the world. They can just react to their environment. So they were actually very interesting to roboticists in the 1970s and 1980s. And we're kind of continuing that thread of research. Fabrication and assembly sequences and processes, and kind of adaptive forming processes, as well as interactive and collaborative fabrication processes. So Giulio was actually an iTech student, and he came up with this concept for a robotic weaving process, and he's actually going to present at ACADIA tomorrow morning. So I really encourage you guys to come to his presentation to get maybe more information about the kind of background and the process and how it's working. But basically there's kind of scanning and a kind of logic of behavioral agent-based model, which allows him to weave on what he's previously been weaving. This is another project that was looking at the kind of research trajectory at the ICD, which is, of course, plate typologies. So can we use the robot to do more than just process the parts? Can the robot actually be assembling? And how do we design for the conditions of robotic assembly? And also use scanning to integrate the whole workflow so that we're responding to the tolerances on site. We can also use behavioral robotics as in a kind of adaptive forming process. So this was actually work from our behavioral robotics course that just finished about a month ago. And in this case, we're also looking at kind of gesture recognition and kind of online robotic programming to kind of control a robot, potentially to implement it in a site such as a construction site, which is unstructured, and therefore it's better to have kind of these online and adaptive processes. And tomorrow morning, I'm actually going to present another project, which was about interactive fabrication. So a human and robot collaborative process, which was a project that the ICD did with Autodesk Research, in which we had untrained people come to the exhibit, get an Apple Watch, and it would basically lead them through a kind of interactive fabrication process with the robot. So for our workshop, we were interested in kind of taking the process further in kind of 4 key themes: material behavior and fabrication-informed design. So developing methods, whether they're agent-based, that obey both kind of the conditions of bending active geometries, but also robotic constraints. Using scanning and machine vision to import information about what we've already constructed. Online robotic control, so connecting directly to the robot, and behavioral fabrication, so developing behavioral methods of design that we can upload directly to allow the design to be kind of emerged through the process. So we worked both digital and analog, so these are some of the hand models that we made. And then we implemented kind of a scanning project. So the whole weaving workflow was kind of working by the end of today. So here you can see we're using also a Connect to scan all of the kind of geometries. And this is sped up. Obviously, some of you might have gotten a peek into the actual fabrication speed. So if we continue the development on this project, I think that's the next thing that we'll look into. But basically, we finally completed a woven prototype this afternoon. And it was really great to work with everyone in our workshop, so I want to say thank you. I want to also say thank you to Giulio for teaching with me. And we hope to continue the work. Good luck with the adapter.
Thanks a lot, Lauren. That was amazing work. Luckily, I've got a Thunderbolt connection instead of VGA, so I should be a little bit. All right. So once again, thanks for the organizers for allowing us to to have multiple workshops here, and thanks for the participants and the leaders of each of these workshops. I'm going to talk about 3 different workshops that we ran, and they each had different principal investigators and slightly different focus, but you'll see a continuing thread of a lot around optimization and exploring different ways to deal with digital information and run it through a design optimization and ultimately an exploration or a fabrication process from there. So the first one up is led, as Wes said before, by primarily Nathan King, but also Gustav Fagerstrom and Stephen Lewis and Nick Coate. And this actually is kind of a continuing trend. Long span, really thin structural members, small robots making big things instead of big robots making small things has been the theme for these. We ran a workshop at Robotics and Architecture in Sydney back in March. There was another one that built upon that research at Smart Geometry over in the Nordics. And then this is the third that adds another level of information on top of that. So instead of optimizing for simply structure or then getting into different species based on the structural capabilities of each type of wood, now we're combining those and getting into changing the form, optimizing the form based on structural analysis, and then adapting and configuring based on a feedback loop with different types of material. So this is the workshop as it progressed this week. So the primary thing that we're dealing with is essentially a space frame type structure that's being designed by the overall group. There was a group design project that led to the agreement on pursuing one design alternative, and then going through that process of refinement and structural analysis and finally fabrication. So the analysis package that actually Steve wrote was a connection to GSA OASIS, so the structural analysis application that primarily Arab created and a lot of people are using around the world. And that is connected to Dynamo as a computational design tool for geometry and sort of the overall program flow. So this is a quick video of that process. Let's see if I can run that. So you can see Dynamo on the left, so standard kind of visual programming environment, driving this analytical tool directly to understand how the overall form is going to behave. In this case, it's a span of about 15 feet tall, and it's basically a big cantilevered structure. So the base is essentially weighted down or a moment connection to the floor, and then it's just spanning out on an angle from there. So you can start to see the deflection. You can start to see where the actual stress is going to be concentrated along the way. And they were able to use those results to directly inform both the topology of the shape and then the species of wood that was going to be used for the rods. So further refinement in Dynamo. And as I mentioned, the actual process, and this is primarily from Nathan King and Nick Coate, was keeping the actual tool in stationary and moving the part as opposed to moving the tool around the part. So in this case, it's basically a sort of a spinning milling bit that the work piece, this node is actually being dropped into, and what you're using Dynamo for is to compute the angles. So for each one of these nodes, computing the correct angle and configuring that. So it was about 260 nodes that were created, each unique, all about, I think, primarily 6 valence connections. So you've got an interesting sort of a conjunction right in the middle there. And obviously indexing and numbering is very important in that process. So the participants ran through that process of design and then fabrication of these, and then assembly is ongoing. And then actually Robert Solovione came in and said, you know what, I have a great way to create the rods in a digital way as well to cut down on human error. So we actually use the mill today to lay out the rods and then index them. So figuring out rod lengths, which are all primarily different, stack them in the tight configuration, and then use the mill to chop them to the right length. And then the assembly process is ongoing, kind of in the same tradition Dave mentioned, sort of aim high and get pretty close by the end. So I think that's ongoing with the team. This is basically the process that we've been going through. So shifting gears, so this is the next one. This is primarily led by John Haymaker and Mohammed Asl, and another set of people from Perkins and Will. And this is an interesting kind of a multidisciplinary project called Design Space Construction that's been going on for a number of months now, and it's coming to an interesting point now of coming together and defining the agenda and testing that in workshops like this, which is pretty interesting. So super well-attended workshop, standing room only. It was getting pretty hot in that room, I'd have to say, just from the level of energy and people and computers in there. But Design Space Construction is a multidisciplinary community of researchers and practice aimed at teaching, testing, and improving design generation, analytics, and optimization methods. This is some great prose from John earlier today. So, and you can see the main goals are to maximize experimental, ecological, and economic value of designs. So proving things analytically, not just based on subjective kind of feeling, and make decisions with confidence. So all these are 3-day workshops. The first day was really about learning about this process and methods, formulating basically a design, running through that process, and then exploring that in multiple ways on the 3rd day and presenting the results. So the team came together and learned the tools. They went through basically an initial design exercise. In this case, this was a single room that needed to be optimized, like a single classroom that needed to be optimized for daylight, energy, and views, using different analytical tools combined and tightly coupled, using Grasshopper and Dynamo together. So, and then sort of managing that information all together. And then the team actually went into using a space plan generator. And this is an interesting development between kind of a triad between Perkins and Will, Georgia Tech, and then Autodesk, developing pretty interesting techniques to understand how to lay out spaces. Again, a lot of academic research over the last 30 years, but never really come together with this level over time and in a tool that someone can use outside of an academic environment. So that's ongoing research that's happening and was tested by this audience. So second day, team worked some more, broke into smaller groups of 3, and then went into looking at another design exercise and looking at machine learning to understand how to take energy analytical results and apply them more effectively to a design. Basically, you can get very fast iteration through many different design alternatives using these types of techniques. And then the last one was, again, like a more detailed design exercise of a child care center. So pretty interesting work coming out of that. And primarily it's not about running the analysis, it's about how do you use those things as the language and interpret the results more effectively to make decisions. And then, of course, running through multiple options and evaluating them. So lastly, we have Computational Bim in Practice, which was Conrad Saban and Nate Holland, Conrad from Grimshaw and Nate from MBBJ. And it was really about how do you use computational design tools like Grasshopper and Dynamo and now Flux together in practice to solve real problems and get essentially the people that are working on the design and exploration tightly coupled into the production process so they're not handing off tools downstream or details downstream and information gets lost. So a lot of space planning, a lot of blocking and stacking, a lot of view analysis for particular room layouts, and primarily learning how to create these tools and use various analytical techniques. Pulling information out. We have so much information in Rhino and Revit and all these other places. How do you pull out the information you need and use it? And actually talking about tools like Bumblebee, which is a pretty interesting plugin on both on Grasshopper and on Dynamo. So more space planning. The team actually got into another tool that Conrad just created a couple weeks ago called Mandrill, which is all about, again, mining information. So much of this is about creating dashboards and exposing information that's there, that's latent, that's not visible. So this is actually using web technologies like D3 and a lot of JavaScript connected into visual programming platforms to do a lot of graphing really simple and easily in a way that it can actually be used to create interactive dashboards without having to write a whole lot of code. That's the great thing about a lot of these components is you can take them off the shelf and integrate them and you don't have to do as much work. So standard kind of parallel line charts and things like that are pretty easy to create that way. Then they got into collaboration and interoperability between Rhino and Grasshopper and Dynamo and Revit, and looked at Mantis Shrimp, which is basically on your client machine connecting information. And then they started looking at Flux, which is all about taking information from one source, telling this online service what you want to propagate up to a cloud service by these data keys, and then pulling it down through a variety of other clients, like it could be Revit, Dynamo, SketchUp, whatever, Grasshopper, doesn't matter. But in this case, looking at site, pulling in topographic information using Dynamo, and then populating that in Revit were kind of the areas of practical use of computation from that. So with that, I want to talk about just one more thing, and that's we have a new space. So I really love the facilities here. They're amazing from a fabrication standpoint, and also I was just at ETH, so seeing some of the work that Dave and Russell have been doing has been really amazing. We just opened up a new office in Autodesk in Boston. We moved downtown, and part of that is this thing we call the Build Space, which we have a similar space in California called Pier 9, and it's basically a place to collaborate. So if you have interesting research you'd like to do, you can apply and basically submit a proposal as an individual or as a team of researchers and come on site, use these facilities. They just opened up like 2 months ago. And we have robots, lots of robots. We have a gantry crane, lots of materials, lots of kind of fun equipment to use, and interesting work that's happening right now. So definitely encourage you to take a look at that if you're interested, or if you're in the Boston area, stop by and we'll talk. So thanks a lot. Really appreciate the work that I've seen the last couple of days, and looking forward to the rest of the conference. Thanks.
Okay, so we're going to invite the four that just presented to join us in a panel discussion now on some of the work. Well, thank you all for presenting your workshops a little bit more in depth and some of your own research work. I think it brings up some good topics that I feel like are going to come up again and again in the conference, and things that we're going to end up just beginning to discuss here. But a few things that came up in different ways. I heard lots of discussion where we're talking about different ways of construction, different ideas of efficiency, optimization, even the data, and how you even go about assessing what you choose to look at, or even the things that end up being down the line and how that works with us. So I think Wes and I are going to ask maybe questions specific to each of you, but also something that hopefully ends up being, a question feel free to answer as well if it was asked to somebody else, because I think there's interesting cross-pollinations that could happen here. So Dave, since you went first, we'll throw the first one at you. And Wes and I were talking about this with you earlier. One thing we always admire, particularly when you're doing workshops, is that you jump into something you've never done before and really kind of fly at it pretty hard. And I think something that ended up coming through your presentation, but also what you're doing, there's clearly an interest in a feedback loop. And I think this goes in the production and the interest in how to efficiently produce the roof that you guys are all working on right now. And I'm kind of curious now, as we look at the really complex feedback loops, where that sort of definition of what ends up being an efficient form of construction lies in that kind of spectrum, where in one case you could resolve it all and end up programming for that and provide a bunch of analysis, or in the other case you're actually doing things where you don't know how strict the slump is going to be. You don't exactly know where that is, but in the end you end up with something that's perhaps even lighter because you've forgiven that. So I'm curious about your relationship now to thinking about modes of construction as being efficient or feedback, and maybe those definitions are shifting for you.
Wait, which one is it? No, absolutely. I mean, I think there's two backgrounds to my practice. So Supermaneuver with Ian Maxwell. One is that both he and I were working for Starchitects, so I for Daniel Libeskind and he for a variety of Starchitects in London, where we just had such big budgets that doing things uniquely was a given, and you could solve the problem by throwing money and people at it. So stepping away from that and having your own small practice and clearly much smaller budgets, then the Australian spirit of kind of looking for bang for your buck really comes through. And so we knew that having control of the computational tools and to some extent, or certainly having a great awareness of the fabrication tools would hopefully lead us to not have to give up quite as much of that uniqueness, or even maybe grab more, but having to take into account the realities of trying to build buildings in situations where you don't have two robots or you don't have whatever it is. So almost all of the techniques leverage in one way or another an attempt to use the computation to minimize either the amount of doubly curved formwork pieces, the amount of scaffolding, the amount of potentially just logistical time on site in order to realize something which in its background has uniqueness as its aim. Uniqueness for us driven potentially just straight by will, that we just like strange things, we like non-uniform weird things. Because we like non-uniform weird things, we make problems for ourselves, and therefore we're kind of obliged to solve them in order to make them even vaguely viable. And so inevitably we end up talking about efficiency and rationalization and minimization of materials, but we don't just do that. We do that in order to buy credit that we can then spend on the willful, fun, spatially exciting, and otherwise thought of as maybe exuberant or ostentatious things. So the idea is that if you're super rigorous and efficient, then you can have more fun. It's not the kind of German rigor of, yes, this is the right answer. I haven't offended enough people.
It may be one of those things though where I think it's a little bit where the efficiency goes into the process, right? Or where one would say, you know, in terms of the design versus the behavior.
You're right. Reduce some of the other people's work to make it happen.
Well, maybe I'll jump in on that. I mean, Brandon, your workshop definitely kind of, as you indicated, stands out a little bit as being outside of maybe some of the typical software and fabrication workflows, but I think it's also really interesting because not only bringing in a physics-based performance side to the equation, but looking at historical precedent as a way to kind of project how these things would go forward. I mean, I don't know if you want to talk a little bit more about how that plays into the projects you undertake, both in research, but I mean, we've all done a lot of workshops. Most people in this panel have done more than a few of these, and how you take that on as being something to do with a group of students in a pretty short period of time.
Sure. I mean, as method, our research method's pretty straightforward. We mine knowledge from the past that's been lost to us in certain ways based on certain ideologies, and we attempt to reapply or translate that knowledge into contemporary practice. And all of this began at, I would say, one particular moment where I witnessed Mark Jarzenbeck present his Global Histories of Architecture book, and he made the claim that every great civilization throughout our history has constructed their architecture in stone, raising the question, why are we not so good at carving in stone today? Does that mean that we're not doing great architecture? So that one little spark for me also happened, and Jim Durham, I think, is in here from Cora Stone, so Jim will probably disagree with that statement, but we're working with Jim in stone, so we're excited about that. But that little spark for me meant that we could have the opportunity in the late 2000s to move away from the assumption of working with sheet materials to produce patterns and thinness. So while you're talking about efficiencies, we're not necessarily looking for volume as a way of being wasteful, but asking the question of when you remove those constraints, which might be industry-based, are there other possibilities that emerge for architecture? And I guess at that moment, I worked under the realization that really to engage this problem, you have to look backwards to be able to look forward. And you probably see that way of conducting the method of research in a variety of people working with stone, by the way. I mean, Block Research Group, I think, has a very similar, do you know their slogan? Or we shouldn't be advertising that anyway, but but yeah, I think that method has been quite productive for me. And the Moai, I mean, the Moai, the realization, I'll talk about that later in the ACADIA paper, but it was such an extra-disciplinary thought that carried with it all the weight and intelligence that is super-disciplinary, dealing with gravity and form and able to perform a task. That is architecture at its essence. However, the megaliths that we're constructing are more spectacular based as opposed to pragmatic or efficient. They're not efficient in any way, right? Although they are very easy to move.
I'm wondering, Lauren, if you maybe want to jump in on the end of that comment that Brandon was just talking about in terms of forms and reacting to that, because I think, it's very clear in the research that you present, the precedents as well, the work you've been doing, the kind of emphasis on behavior in construction and understanding materials and their logics and how that actually applies to the way of making. And I think the workshop definitely emphasized that sort of performance.
Yeah, I was going to say that it's exactly as you described, looking backwards or questioning conventions and where they emerged and looking backwards to see how to move forwards, especially when it comes to kind of standardized building materials, because we're relying on production chains which are producing non-anisotropic or standard materials, and then we're relying on logics of discretizing them, and we're basically questioning if those are the fundamental. If we remove that constraint of working, what are the new possibilities enabled in terms of building systems? Looking even back to kind of vernacular building processes that weren't about a predefined plan, but about a logic of action and reaction to what you made previously.
I wonder how that folds into some of the things that you were discussing in terms of some of this information that runs latent that we can't necessarily see, and our ways of kind of bringing those to the forefront through what we're choosing to analyze or through what we're actually putting as the inputs into some of the optimization programs and things like that. I think the kind of idea of what is chosen as the data inputs or what we're now focusing on, where it can be something like gravity or the alteration over time or client needs, construction, the values, and where we choose that sort of connection through.
Absolutely. I think, as designers, we tend to look at things like geometry and partie and how things we can explore and design very interactively, but there's all this latent information that exists all around us, either environmental information or the program, just that exists that you're trying to solve for, or even just material properties. Some things that we know objectively, but they're not really part of the design process in many ways, or at least the ones that we went through in traditional design sort of education. But now they all exist, and they're there, and they're available, and they should be part of the lexicon and the way that we teach design and the way that we practice design. So I think a lot of the practice that we see now, you can, for a really small amount of money, start to instrument your building as it exists, add sensors all around. You can look at occupancy. You can do things that really understand how people are utilizing your space. And it's not just about post-occupancy studies. It's about real-time use and how someone is actually using the thing that you design, not how you think they should be using it. So how can that inform the design process? Then you also get into things like materiality. So the really interesting work that I've seen over the last 10 years has to do with the design of materials. And Lauren, you've really done a lot in that space, and with Occam as well. How can you push the materials farther? How can you use non-traditional building materials like carbon fiber, or use very traditional building materials like stone in different ways? That's where things get interesting. And it's not about throwing more steel at the problem or more panelization. It's like, how can you use the things for their inherent structural capabilities, but in different ways? Anybody else?
Maybe going back to that then, both in what Lauren was saying with the vernacular and Brandon with the references to some of the things in the history, does it seem like there's a moment where what we're choosing to sense or push in is things that perhaps in earlier times were what we were embedding into our designs, and then maybe we lost a focus on that, or we, of course, went for other things, and now there's a return? Do you get that sense, or do you think it's just a matter of what we're kind of shining the light on at each moment?
Well, I think, to that point, Matt, you're raising a topic that is very exciting at this moment in time, which is where the designer is becoming in tune with all these other bits of information that really we should have at our disposal. However, in the conventional formalist logic of architecture, and I will call it the traditional sense of creating design. Those things are abandoned. And I'll just, an example, produce plan, produce section, label it with a material, move forward. That was the method of design with which I was born up in. And now we have the capacity to re-engage more bits of knowledge. Now, that is not to say that this is a somehow brand new topic, because I would say that that synergy between those two worlds is exactly what happened when all of my favorite architects existed, which were master makers. I mean, if you look at Felix Candela, he was doing this at a material scale. If you go back further to Philibert Delorme, he was simultaneously doing this with methods of drawing in synchro with methods of construction. So I think it's that the synapses reconnecting in some ways, which somehow industrialization, the way that we've, since we're talking about workshops in a sense, the way that we are constructing our division of discipline between those which think and those which make has created this vacuum of possibility that now is being filled in by all of these potentials. So I think it's an incredibly exciting time to be. I don't know if this had anything to do with educating architects, but I'll tackle that. I think it's an incredibly exciting time to be studying architecture.
Yeah, I mean, following up on that, maybe Brandon, I mean, Dave, you're obviously currently at Zurich in the block research group, and they're, I mean, you guys are looking at kind of an entirely new level of integrating structure, but now acoustics and so many other different inputs, which I think are available by these new tools, and how at some level it's also designers having access to this feedback that didn't really exist and being able to use it in a closed loop way, not necessarily having to meet with a consultant, but literally having a plugin that can kind of start the process. Certainly doesn't replace the expertise that consultants bring, but I mean, I wonder if you could talk a little bit about how, I mean, your work has always, Dave, been really focused on kind of pushing the limits of optimization and form finding, but I know there was always an attempt to saturate the design process with these inputs. And maybe just kind of, if you could project like what you think the next thing in that area is for this type of work.
Yeah, no, that's right. I mean, the original motivation for me even starting to write code at all was simply to try to have as many design arguments as possible, that things like sun paths would have to fight it out with where is the front door, would have to fight it out with how furry is my ceiling, or any of the kind of things from highly rational to completely abstruse reactions. And so I'm extremely excited to see the sorts of things that Matt showed, that more and more, so originally it was all custom-made tools and code would allow these things to have to put pressure on each other. So I think all of the plugins and attempts that Autodesk is making to bring through Dynamo and other things, that these things can very literally have to fight it out, to me is extremely, extremely exciting. And then now it's actually over, and it's actually the right way. That the architect's role then is to figure out what the right way, the right rules of engagement are, what the protocols are, in what way should a sun solar path, in what way should that make a difference to our building? Hopefully it's a lot more than just really efficiently making the shade diagram to show to the planners, or that everybody's site analysis now looks exactly the same and took 10 minutes and nobody had to think while it happened. To me, it's really about in what ways can we force direct interaction, not a really loose, poetic. Architects, of course, has always been amazingly good at juggling lots of balls and being able to claim that because I was inspired by the sunrise when I camped on the site that morning, that therefore my building is so environmental. I think it's really great that the numbers will hold us accountable. I think it's really great that we have those numbers and we can plug them in and make these things more rich and more attuned to each other. Where I do think efficiency... Or disregard them entirely as well, absolutely. Yeah, totally. But also have to be forced to say, yeah, it's true, the sun sucks in this building. I would have paid attention to the sun, but sadly, because I live in Uruguay, then it doesn't do anything. And my total design agenda is over, but I have to, and then I'll have to fill the void with something else.
Oh, Well, we are running a little bit out of time, but we have 7% left. We would like to also allow, if there's questions for anyone on the panel, coming from anyone in the audience, perhaps even people that have been in the workshops now asking Brendan questions, or anyone who'd like to ask anything. Or not.
Again, great presentation, everyone. I think it was great. I still sort of run into the problem of relationship between the thinker and maker, right? When you have control over that little piece that is precious, that works fine. But when you are involved in a large project that you cannot control, right? Is our ultimate goal replacing them, right? I mean, in a way, we fantasize about that. Let's be honest, we do.
Replacing who?
The makers.
Oh, no, I don't think so.
No, right. So when we're talking about great projects around the world that hundreds of people involved, the code is just one part of it, right? And how do you think we negotiate all those interests? I think the part of that is kind of data that's embedded that begins to open up different way of discussing. But I'm not sure we talk about that enough, about that collaboration aspect of how you work through these things. I think there's a great potential there as well, especially when you combine that with kind of material feedback that we're now able to crack. What is that? What is that? Like, is it more of? It's almost like children learning, isn't it? Like, what kind of material feedback on top of these digital processes start teach each other about the design, right? And I think it's something that I'd love to just, as a very exclusive group of architects really in this room, to really think about and have a discussion.
Okay. Yeah, I think there were about 4 questions in there, but yeah. So I think getting back to the topic of collaboration is inherent. And none of us are the sort of ivory tower. I will, through sheer force of will, create this thing. There's always a group of people around you. But one thing about collaboration is it requires understanding about where other people are coming from, and this idea of the design and then the work, the making, really is a fairly artificial construct. And I think if you go back to obviously Renaissance times or anything else, the master creator is a really interesting thing. But even now, if you're talking about a design team of professionals that each have different skill sets, having respect for where the people are coming from and having gone through their work process, be it the acoustical analysis engineer or the guy that's laying the stone for the facade, it doesn't matter. You need an appreciation for how they're working and what their needs are, and you can't just say, "Well, figure it out," because you're giving up part of your sort of process and your responsibility. I think specifically related to craft, that's something that I think personally is a really important thing for designers to really understand. If you don't understand how things are made, you really can't call yourself a good designer. So getting out and actually making something, even if you don't actually execute the work yourself later, gives you a firmer appreciation for the people that are doing that work. So, and therefore a better way to collaborate.
Maybe I'll take on one of the other questions that was in there. So it seems like you're basically asking or making a provocation of, yes, that all of that stuff's great, and clearly you're in the room, so you're a supporter in some way of the various agendas represented, but does it scale? In what way can we distribute this to the rest of the world who don't have robots with sensors and don't have all of these things? So perhaps it could be an accusation that this is, yes, great, but just very boutique and perhaps only ever going to be the tip of the iceberg. And I would contradict that, or at least explain that in my opinion, that especially now as we start to move to more responsive approaches where we start to use scanning and so forth to deal with tolerances, that actually applies exceptionally well to places where people build really, really badly. Not to mention that various forms of adaptability and computational responsiveness would also work extremely well in places where people build extremely badly and things don't go exactly as planned, that having an inherent level of responsiveness would be a really resilient way to practice in those kinds of places or in those kinds of projects, which, let's face it, anyone who's really built means every single project, things don't go quite right. And the traditional design process is finished normally, right? The documentation set is in, the tender's gone through, you're at arm's reach from the project, but perhaps the kinds of thinking that does have conditionals embedded, does have an adaptability embedded, could actually help to straddle those contractual divides and allow our projects to roll with the punches a little bit more, which might make them actually far more scalable approaches than, in terms of direct technology, but the underlying logics should actually help a lot.
Is there another question?
So, given the past implications of affecting material and resources, right? As Jezyk was given on like how you design and kind of work with problems. If you're saying so, you have to get to know how to make things. If you can start to engineer these materials from a molecular level, synthetic biology getting a little bit more robust. Can you guys give some notes on kind of your take on how that might start affecting our professional academic
That's you,
That was
Lauren.
very synthetic, yeah. I mean, for me, it's not about identifying specifically synthetic biology, but about fundamentally questioning production chains and where the innovation can come. And I don't know that it's necessarily academia that would answer that question, or a professional commercial entity.
Well, we all do.
Yeah.
There's enough questions for us to all get together.
Yeah, I don't think I'd really go as far as synthetic biology. I think I'd go more towards, if you look at the embodied energy problem is probably a bigger one to think about. Like if you look at the amount of miles that materials travel to get to a work site, it's pretty significant. So if you can think about local sourcing of materials that may actually exist, you just have no real way to source them because of the actual sort of chain that you typically are dealing with. Or if there are ways to obviously reuse materials or adaptively reuse them in a potentially creative way, I think that's a more interesting problem than, again, like through sort of sheer force of will, I will like literally fabricate this new material, which, I mean, if you look at the amount of energy that goes into just driving robots to cut the things that we could have cut in a different way, in a much more efficient way, from an environmental standpoint, again, like I don't know if throwing more technology at a problem like that is the right answer. It might just be looking at what is immediately around you and reusing it in a better way.
I think we have time for one more question. I saw one here. Yes.
In your opinion, what is the key limitation in digital fabrication that needs to be resolved over the next 10 to 15 years?
I think the architect, actually.
That's great.
I mean, they're the biggest problem, I think. Right? We're so stuck. I mean, we have a professional mandate, which has siloed us into particular understandings of what our role will be, and perhaps it's the role of the architect that's the biggest problem. But the tools are there. I mean, robots are not new, right? Wes, can you elaborate?
Mid-50s.
So it's not the tools, it's not the fabricators, it's not the makers. I mean, I don't think it's about asking contractors to somehow make things better, that somehow our contractors are not good enough. It's that this disconnect between architects constantly creating things that cannot be made in a way, and really having the pushback from receiving that feedback. So this is really getting to the question of being open to your collaborators and asking those questions. And until we're open to the realities of that method, I think we are the weak link.
That, and we're going to run out of animal metaphors to name our plugins.
Yeah, I would also say that the construction industry is incredibly risk averse, and it's not just about the lack of incorporation of robotic fabrication. It's also about data monitoring, like on a construction site, or keeping track of parts as they're being fabricated. And I know, so when we were doing the Autodesk project with the kind of interactive app, one of the only precedents was the shop building in which they had an app to kind of track all of the parts as they were being fabricated, and then could actually know via a scanning process where those parts were as they were actually on site. But looking at this kind of more integrated workflow, connecting, I think, going back to the point that was made earlier, how do you computationally link every interest that goes into the production and design of a building on a large scale?
Mm-hmm. Yeah.
Yeah, I mean, more seriously, I think a big job that we have as a community is to get our clients to be willing to trust that we can bring back a lot of the work from the contractors. We can bring back shop drawings. We can bring back a lot of these things which people are not accustomed to paying for, or at least not accustomed to paying us for. And also, there's a great deal of faith, right? We can say, trust us, trust us. We've done so much great work. The things are so well understood and quantified that you won't have to pay as much down the track. And that's a really easy thing to not be believed at all, right? So right now, all of the complex fabrication guys are getting paid by contractors, not by clients. So as a community, we need to, one, put our money where our mouth is and really do it if we say it, because otherwise we'll ruin it for everyone if it does turn out that they have to pay twice, and we told them that they didn't. And also to really try to take responsibility back, right? As a profession, we've shrunk massively because we thought it was awesome that we could sit back and just be the artists. And we gave up to project managers, we gave up to quantity surveyors, we gave up to all of these new fragment professions who are willing to take responsibility and therefore took big chunks of the fees. We should now be willing, as part of our attempts to try to grab hold of the whole production chain, also acknowledge that we have to take that responsibility. We'll have to take insurances out in order to live up to that, but then to deliver, and in the process to try buy back a much bigger role and a much bigger slice of the initial fees, also towards realizing much better and richer projects by not having this kind of sequential chain of information loss, basically.
I think that actually sets it up as a good challenge and reflection on the workshops that just happened, in terms of looking not necessarily even at the details of which machine or material or software was used, but the kind of way of working that came out of all of these, and even in the intensity of the 3 days, the way that can actually end up pushing back on the way that we ended up working. So with that, I want to thank Lauren, Matt, Dave, and Brandon for being part of our panel, and for all the workshop leaders that were involved in all 7 of the workshops, as well as the attendees and the energy that came this week, and everyone who made it possible for all of you to be here. And with that, we'll conclude this panel and launch into the ACADIA conference. Thanks all.